Welcome to Hypothesis Testing Demystified, a practical guide to statistical inference. This opening slide shows two overlapping distributions, balanced on a scale to symbolize the null and alternative hypotheses, and sets the stage for how we'll reason about evidence, make decisions, and turn data into actionable conclusions throughout this presentation. This slide contrasts the null as the default assumption with the alternative as the research claim, and highlights the evaluation process. We compare observed data to expectations, using objective tests rather than impressions, then draw a clear conclusion that yields actionable insight based on whether the data sufficiently deviates from the null. Here, we compare directional one-sided tests with non-directional two-sided tests. A one-sided test has more power to detect a change in a specified direction, but requires a precise hypothesis, while a two-sided test guards against departures in any direction and offers broader generality when the effect direction is unknown. This page explains alpha as the researcher's preset risk tolerance for falsely rejecting a true null hypothesis. Choosing a stricter alpha reduces false positives, but demands more evidence. The conventional 0.05 balances caution and sensitivity, and more lenient levels are sometimes used for exploratory work, where discovery is prioritized over strict error control. Choosing the right test statistic depends on your data and assumptions. Use a z-statistic when population variance is known and samples are large, a t-statistic when variance is estimated from smaller samples, and chi-square tests for categorical associations. Matching the test to data characteristics preserves validity and leads to reliable probability calculations. The p-value quantifies how compatible the observed data are with the null hypothesis by showing the probability of equally or more extreme results. It's a measure of evidence, not proof, and it does not tell you effect size, practical importance, or the probability that a hypothesis is true, so interpret it in context with other metrics. Critical values define the rejection region on a test statistics distribution, and they're set by your chosen significance level. The decision process is straightforward. Calculate the test statistic, compare it to the critical value, and then decide to reject or fail to reject the null, while understanding this threshold controls type 1 error across repetitions. Statistical errors in power shape decision-making. A type 1 error is a false positive, and a type 2 error is a false negative, while power measures the probability of correctly detecting an effect. Balancing these risks through thoughtful sample size planning ensures sufficient sensitivity without wasting resources and supports practical decision-making. Power analysis helps optimize sample size by combining three inputs: effect size, significance level, and desired power, so you avoid being underpowered, which risks missed discoveries, or overpowered, which wastes resources. The goal is an optimal sample size that yields reliable inference, ethical resource use, and efficient experimentation. Moving beyond mere significance, we assess practical magnitude using effect sizes and plausible ranges with confidence intervals. These richer statistics quantify real-world importance, provide a range for the true parameter, and support reproducibility and informed decisions, rather than a simple yes/no outcome from a p-value alone. Valid inference requires checking prerequisites like random sampling, independence, normality, and homogeneity, then detecting violations with diagnostic plots and formal tests. When assumptions fail, prompt actions such as transformations or non-parametric alternatives help protect conclusion integrity and uphold the reliability of downstream decisions and recommendations. Comprehensive reporting builds trust by documenting hypotheses, alpha levels, test statistics, exact p-values, effect sizes, and confidence intervals, and by disclosing exclusions and analysis paths. Transparent, rigorous reporting reduces bias, enables replication and meta-analysis, and ultimately fosters cumulative knowledge and credibility in scientific findings.